Okay, let's dive right into this explainer. We've designed this specifically to be your ultimate visual study guide for acing that upcoming geography exam on solar radiation and temperature. Look, if you've been staring at your textbook trying to figure out how on Earth our planet actually manages its heat, you are absolutely in the right place. We're going to break down exactly what you need to know, stripping away all that extra fluff so you can walk into that test with total confidence.
Here's our game plan for today. We'll hit the essential terms first, then we'll balance the heat budget, figure out the factors controlling global temperature, and finally, we'll decode some isotherms and maps.
All right, kicking things off with Section 1, Essential Geography Exam Terms.
Okay, the absolute crucial point here is that insolation is really just a fancy mashup of the words incoming solar radiation. Seriously, whenever you see this word on the test, just picture the sun's immense energy traveling through the literal vacuum of space and smacking right into the top of our atmosphere. And remember this key detail, it arrives in short waves. Our atmosphere is mostly transparent to these short waves, which means they pass right through to warm up the Earth's surface.
Now, if insolation is the income, albedo is kind of like a rejected deposit. It's the solar radiation that gets bounced right back out into space by things like clouds, fresh snow, and massive ice caps. This energy never actually heats the Earth, not even a little bit. It just hits a super bright surface and reflects away like the Earth is wearing a giant planetary mirror. So, when you see this comparison on your exam, remember the difference all comes down to wavelength and direction. The sun sends those short waves down to heat the surface, but then the heated Earth essentially becomes a radiating body itself. It sends energy back up into the atmosphere, but this time in the form of long waves. We call this terrestrial radiation, and believe it or not, it's actually what heats our atmosphere from the bottom up. It's just a beautifully elegant system.
Moving right along to Section 2, Balancing the Heat Budget.
What's really cool here is that we can treat the entire planet's atmosphere like a giant accounting ledger. Just look at the journey of this sunbeam. The Earth gets an income of exactly 100 units of insolation at the top of the atmosphere. And because our planet doesn't just continuously heat up or cool down over the long haul, we have to track exactly where every single one of those 100 units is spent or saved. At the end of the day, the budget absolutely must balance out to zero.
Let's simplify the math so you can memorize this ledger. 100 units come in, boom, 35 bounce right off immediately. That leaves exactly 65 units that actually enter our Earth atmosphere system. You've got 51 absorbed directly by the Earth's surface and 14 soaked up by the atmosphere itself. But again, because the Earth isn't boiling over, those exact same 65 units are eventually radiated completely back out to the freezing void of space. You know what? Just drill this number into your memory right now. 35. This is our global albedo. It's the exact number of units reflected away by the tops of clouds and polarized caps before they can even touch the surface. If your exam asks what portion of solar radiation is lost to space without heating the Earth, your answer is always 35 units.
And then we have 65, the magic number of balance. This is the total number of units absorbed by the Earth and the atmosphere combined, and consequently, it equals the exact amount that eventually gets radiated back into space as terrestrial radiation. It's what keeps our planetary bank account at a perfect, life-sustaining zero balance.
All right, Section 3, Factors Controlling Global Temperature.
Since the overall planet is balanced perfectly, we have to ask, well, why are some places freezing while others are sweltering? The key takeaway for your test is to master these 5 variables. Latitude dictates the angle of the sun's rays. Distance from the sea matters because water heats up and cools down way slower than land does. But definitely pay special attention to altitude and the normal lapse rate. This is the rule that proves, for every 1,000 meters you climb in elevation, the temperature drops by exactly 6.5 degrees Celsius. Write that 6.5 number down for sure.
And finally, Section 4, Decoding Isotherms and Maps.
Let's apply all this theory to the really complex diagrams you'll face on test day.
Think of an isotherm as a thermal fingerprint on a map. Iso literally means equal, and therm means temperature. So if you trace your finger along one of these lines across a map, every single city, mountain range, or ocean you cross is experiencing the exact same temperature at that moment.
Take a close look at just the northern hemisphere on this January map. Do you see how the lines aren't just straight horizontal bars? They wildly bend to the north over the oceans, and then they take these really sharp dips to the south over the land masses. The northern hemisphere just has way more land than the southern hemisphere, which makes these bends incredibly dramatic to look at. Now, this visual deviation happens because land cools down incredibly fast in winter compared to water. In January, the air over those massive continents is just freezing, literally dropping to a bitter minus 20 degrees Celsius out in the Siberian plain. So the isotherm bends south to find that cold air. Meanwhile, warm ocean currents, like the Gulf Stream, are keeping the waters of the North Atlantic relatively mild, which forces the isotherm to bend way back up north.
Now compare that exact same map to July. See how the isotherms suddenly flatten out significantly and run almost completely parallel to the equator? Why does that happen? Well, because the northern hemisphere is being completely bathed in summer sunlight. You can literally see these massive heat pockets building up over the land, especially across the Asian continent and North Africa, pushing well over a scorching 30 degrees Celsius.
Before we show the final map, I want you to test yourself. Based on everything we've just covered about how land heats up quickly and cools down quickly, compared to that nice moderating effect of the sea, where on Earth would you expect to find the most violent swings in temperature over the course of a single year? Let's see if you hit the nail on the head. This map charts the total range of temperature, meaning the difference between the hottest and coldest months. And what it reveals is this massive bullseye of extreme variation sitting right over the northeastern part of the Eurasian landmass. Because this massive chunk of land is so deeply isolated, just thousands of miles from the moderating influence of any ocean, it suffers from a phenomenon known as continentality. The lack of nearby water means there's absolutely nothing to buffer the temperatures, causing the climate to swing by a brutal 60 degrees Celsius between the height of summer and the dead of winter. It's pretty wild, and it's a fantastic real-world application of those heating rules we established earlier.
As you prep for your exam, I want to leave you with this one thought to ponder. If our entire global climate relies on that really delicate 65 to 35 unit balance of the heat budget, what happens to our world if melting ice caps drastically change our 35 units of albedo? How would that permanently rewrite every single isotherm map we just looked at? Keep that interconnectedness in the back of your mind, and you will absolutely crush this material on test day.